A future spacecraft could help us learn more about the Big Bang. When Europe starts the Laser Interferometer Space Antenna, LISA, scientists can examine the universe's beginning in greater depth. A few years ago, David Dunsky attended a meeting in Japan where gravitational waves were discussed. Massive objects like black holes and stars accelerate, creating these ripples in space-time. At the time, Dunsky was a graduate student in particle physics, but it looked like he wasn't interested in that. Scientists who study particles try to find the deeper truth behind the physical rules we understand. For a long time, scientists have used high-energy particle colliders to test their ideas. Scientists can discover the fundamental parts of the universe by smashing particles together at unimaginable speeds. These are the high-energy events that happen over short distances. These events also tell us about the universe's beginning, when it was very small, thick, and hot. Dunsky learned during the talk that future gravitational wave detectors, like the Laser Interferometer Space Antenna, LISA, might be able to study high-energy physics. The Laser Interferometer Space Antenna, LISA, has the potential to detect cosmic strings, which are long lines of concentrated energy that may have originated during the creation of the universe. Dunsky, a cosmologist and particle physicist at New York University, became very interested in gravitational wave signals from the universe's beginning and how they might show high-energy physics beyond what current colliders can detect. His shift toward gravitational waves as a way for particle physics to move forward shows how interest in the coming LISA experiment is growing and may be a sign of a larger change. It's been 12 years since a particle collider made a major discovery. The discovery of the Higgs boson at the Large Hadron Collider, LHC, in 2012 completed the standard model of particle physics, the main theory of known elementary particles and forces. Since then, scientists have proposed numerous new theories beyond the standard model. Remember, we can test these theories by building colliders. Physicist Raman Sundram from the University of Maryland said, "In the next 50 years, people are going to build colliders that are 10 times more powerful than the LHC in terms of energy." Testing grand unified theories, on the other hand, would seem to take a collider that has 10 billion times the energy of the LHC, he said. According to these theories, a single force acting at shorter distances connects the three forces of the standard model. Nature lets us see things that we can't make in a classroom. Specifically, the gravitational echoes of events from the beginning of time, when the universe was so powerful that physics beyond the standard model would have been common, may hold the answers. At a table outside, a guy in a white shirt and glasses smiles at the camera. David Dunsky is a cosmologist and particle physicist at New York University. He investigates how LISA might be able to detect early universe phase transitions. Particle scientists like Dunsky and Sundram hope that will happen. They are now looking for a LISA to test their ideas. They came up with the idea for the project in the early 1980s and officially asked the European Space Agency, ESA, to support it in the 1990s. NASA worked together on the project for a while, but in 2011 the Americans gave up on it because of budget worries, leaving Europe to work on it independently. However, in January, LISA finally got the green light from ESA. The agency is now looking for business partners to start building it. The news comes after LISA Pathfinder, a pilot mission that tried the key technologies for the future observatory in 2015 and 2016, was a huge success. LISA will start in the 2030s. Its 3 satellites will tumble through space in a triangle shape about 1 million miles across for 4 years. To measure changes in space-time, they will use lasers to bounce off of golden cubes kept in free fall inside each craft. Isabel Garcia, a particle physicist and cosmologist at the University of Washington, said, "For the first time, we might actually get something directly from that very early epoch of the universe." She also said that if LISA can pick up primordial gravity waves, it will be the first time we see the very beginning of the universe. from the particle physics perspective, that is incredibly exciting. If LISA does find primordial gravitational waves sometime in the next 10 years, it will be a huge stroke of cosmic luck. There will never be a telescope that can show the very beginning of time. Telescopes can see the world's past by picking up light traveling far away. A cosmic screen hides the first 380,000 years after the Big Bang. At that time, the world was made up of ionized plasma, which scattered photons and blocked light. In the early universe, gravitational waves could move easily, but light waves could not. Ground-based telescopes like LIGO and Virgo probably can't pick up on these primordial waves, but LISA can hear what happened before the curtain went up in space. "It's like hearing something through the fog," Sundram said. With lasers, gravitational wave observatories on Earth can detect ripples in spacetime by measuring the distance along their arms. In this case, LISA's arms are the lines of empty space between the three satellites in its triangular constellation. Spacetime gets bigger and smaller. This results in a slight alteration in the lengths of LISA's arms, which the instrument detects by observing the irregular alignment of the peaks and valleys of its laser beams. Removing LISA from Earth's noisy surroundings will enhance its performance compared to interferometers like LIGO, which have successfully detected collisions between black holes and neutron stars. Also, it will be a lot bigger. Its arms will be almost 400 times longer than the surface of the Earth. Still, LISA will only be able to pick up very small changes in distance, about 50 times smaller than an atom. Space scientist Nora Lutskendorf, who works for ESA and oversees the LISA project, said, "It's a pretty crazy idea when you think about it. Because it is so big and sensitive, LISA can see gravity waves much longer than interferometers on the ground. LISA can pick up radiation from a few 100,000 kilometers to a few billion kilometers away, while LIGO can only pick up waves with widths between 30 and 30,000 kilometers. For example, when supermassive black holes, much larger than star-sized black holes, join, LISA can hear them, but not ground-based observatories. Also, LISA's wavelength band is the exact size that scientists think gravitational waves will be when made in the first few seconds after the Big Bang. In the early universe, high-energy physics caused gravitational waves that grew to huge sizes as the universe and space stretched. LISA is set up to pick up waves made in the first 1017 to 1010 seconds after the Big Bang, which is the start of time. At the very short end of that range, there are 1017 seconds. That's so short that it would fit into a second about as many times as seconds fit into the age of the world. There is this serendipity, Chiara Caprini, a theoretical cosmologist at CERN and the University of Geneva, said. It matches the LISA detection frequency band and this particular epoch in the evolution of the universe, which marks the frontier of our knowledge of particle physics. We use the Standard Model to explain how its group of 17 elementary particles interacts with three forces: the electromagnetic force, the strong nuclear force, and the weak nuclear force. But even though it has had great success, no one thinks that these particles and forces are the most important things in the world. In front of a whiteboard, a man in an orange t-shirt talks and makes funny faces. Raman Sundram from the University of Maryland talks about how signs from gravitational waves could shed light on high-energy particle physics and cosmic inflation. The idea could benefit from some improvements. For instance, the Higgs boson's mass needs to be more realistic. This is because the Standard Model tells us how heavy other particles are. Looking at the universe's much larger amounts of energy, it seems random and strangely small. On top of that, the Standard Model doesn't explain dark matter or the mysterious dark energy that makes space expand faster. Another issue is that matter and antimatter behave similarly under the Standard Model's three forces. This is clearly only part of the story, since matter rules the world. One more thing. Gravity. General relativity has to explain the fourth basic force that the Standard Model doesn't consider. Pierre Auclair, a theoretical cosmologist at the Catholic University of Louvain in Belgium, said, "So, a lot of theorists like me have been trying to squeeze the Standard Model a little bit and try to make extensions of it. However, experiments are necessary to test these more general ideas. Auclair comes up with ideas. Nevertheless, I strive to establish connections with experiments to the greatest extent possible," he said. This is what drew him to LISA. These extensions usually lead to different extreme events in the early universe, he noted. Even Garcia changed her job path because LISA promised observational proof for high-energy physics. Gravitational waves could prove the early universe in a way no other experiment can, she said. She looked into gravitational waves and how physics beyond the Standard Model would leave signals that LISA could pick up on a few years ago. A woman in a blue jacket stands outside with her arms crossed and smiles at the camera. Isabel Garcia from the University of Washington recently discovered signs of bubble walls in gravity waves. Garcia and her colleagues published work last year on the gravitational wave signature of bubble walls. Bubble walls are energetic barriers between space areas stuck in different states as the universe cools. As the world grew bigger, this cooling took place. The world underwent phase changes such as water boiling and turning into steam. The change in phase in the Standard Model was pretty smooth when a single electro-weak force split into different electromagnetic and weak forces. However, Dunsky, who also studies topological flaws like bubble walls, said many theoretical versions predict violent events that make the cosmic soup foamy and jolly. We refer to the quantum fields that permeate our world as ground states or minimum energy. As the universe cooled down, new ground states with less energy formed. However, a field occasionally observes its new ground state. Local energy minima or fake ground states that only appeared stable trapped some fields. However, every once in a while, a tiny part of the universe would quantum tunnel into the real state, creating a bubble of true vacuum that grew quickly and had less energy than the rest of the universe. These bubbles are very energetic. They're moving very close to the speed of light due to this pressure difference between their interior and exterior, said Dunsky. So when they collide, you get this violent collision between these two very relativistic objects, somewhat similar to how black holes emit strong gravitational waves right before colliding. Changes in phases in the early universe may also have created structures known as cosmic strings and domain walls, which comprise very long, dense energy lines and sheets. They appear when a quantum field's ground state changes, and there is now more than one valid new ground state. In this case, there may be high-energy flaws near the edges of areas of the universe that fall into different but still good ground states. In front of a whiteboard, the picture shows a woman with brown hair and glasses happily sitting down. Chiara Caprini is a cosmologist at the University of Geneva and CERN. She studies the possible shapes of gravity waves caused by changes in the primordial phase. Dunsky, who has studied the process's visible signs, said it's like how some rocks become naturally magnetic as they cool. Atoms are arranged randomly at high temperatures, but when it's cool, it's energetically better for them to line up magnetically, which changes the ground state. The atoms can line up independently if there isn't an outside magnetic field to guide them. All choices are valid. By chance, different parts of the mineral will make different ones. A magnetic field comprises all the atoms and bends many where two domains meet. He also said that the quantum fields in different parts of the universe must change rapidly at the boundary of these domains. This would cause high energy densities at the boundaries, signifying the presence of a domain wall or cosmic string. If they existed, these cosmic strings and domain walls would have grown to cover almost the whole universe as space expanded. These objects produce gravitational waves as kinks move along them, loops oscillate, and cusps form. However, formation processes in the early world largely determined the energy levels of these waves. If there are any, Lisa can locate them. Lisa can locate them. Echoes of the beginning. Gravitational waves from the universe's beginning will not come to us in neat chirps, like signs from black holes crashing into each other. Since these signs have been around for a long time, they have spread out across all of space. They will sound like they're coming from everywhere simultaneously, like the background hum of gravity. Garcia said, "When you turn on your detector, it's always there." According to Sundram, most people would think that the patterns in this background are just noise. But secretly, there's a hidden code. The spectrum of the background signal, which shows how strong it is at different frequencies, is an important measure. If a gravitational wave signal were a sound, its spectrum would be a pitch and volume difference graph. Lautrec stated that white noise that was truly random would have a flat range. However, the loudest gravitational waves originate from cosmic strings, domain walls, or during phase changes at specific frequencies. Auclair has worked to figure out the spectral fingerprints of cosmic strings. As their kinks and loops change, these strings send gravitational waves at specific wavelengths. Caprini looks into what kind of marks violent phase changes would leave on the background of gravity waves. Sundram and his friends proposed this idea in 2018 and have since adopted it. Another idea is to map the overall brightness of the background across the sky. This way, we can look for a louder or quieter spot than usual. The trouble, Caprini said, is that this kind of signal is similar to instrument noise. So the question is, how can we tell them apart once we find something? Physicists look for the triangles from the Big Bang. Like a microphone, Lisa listens to the whole sky at the same time. If primordial gravitational waves are present, they will be heard. But it will also hear the chirps and howls of merging black holes, neutron stars, and the many pairs of white dwarf stars in our galaxy. We must carefully identify and remove all the other signals to get Lisa to find a background of primordial gravitational waves. Sundram is optimistic, though. "We're not crazy to be doing the research," he said. "Experimentalists will have a hard time. Most people will have to put in much work to cover the costs. It will be hard for thinkers to do the math to get past all the unknowns, mistakes, backgrounds, and other things." Sundram said, "It is still possible. With a little luck." Astrophysics' most important study finds that dark energy may be getting weaker. For many years, scientists have called the mysterious dark energy that flows through the universe the cosmological constant. The most detailed map of the universe suggests that this energy has been changing for billions of years. This picture shows a telescope looking up at the stars on a mountain. The Dark Energy Spectroscopic Instrument, DESI, at Kitt Peak National Observatory in Arizona, has created a massive 3D map of our planet. The regents of the University of California, Lawrence Berkeley National Laboratory, and Marilyn Sargent are in attendance. Scientists have found small signs that the mysterious, dark energy that makes the universe grow faster and faster may be getting a little weaker over time. This discovery might shake up the very roots of physics. If it's true, it would be the first real clue we've had in 25 years about what dark energy is, said Adam Rees, an astronomer at Johns Hopkins University who shared the Nobel Prize in 1998 for finding dark energy. The Dark Energy Spectroscopic Instrument, DSC team, made the new observations. Today, they unveiled the largest ever universe map and conducted numerous measurements. For many researchers, the most interesting thing is a plot that shows how 3 different sets of observations suggest that dark energy's impact may have decreased over time. It's possible that we're seeing signs of dark energy changing, DESI team member Dylan Brout of Boston University said. Scientists concur that inside and outside the collaboration, further evidence is necessary to establish a fact. The The findings support the idea that dark energy is breaking down, but the statistical significance could be higher and could easily go away with more information. However, researchers have found that 3 sets of observations all point in the same interesting direction. This direction differs from the usual view of dark energy as the energy in empty space, which Albert Einstein called the cosmological constant, because it doesn't change. "It's exciting," Sesh Nadatha, a cosmologist at the University of Portsmouth who helped with the DESI study, said. "If dark energy is not a cosmological constant, that's going to be a huge discovery." The origin of the cosmological constant. Scientists led by Rees and Saul Perlmutter used the light of dozens of distant supernovas in 1998 to demonstrate the assembly of the universe. They found that as the universe ages, it expands faster. Einstein's general theory of relativity says that mass, or energy, can expand the universe. Matter and energy, on the other hand, become less dense as space expands because they spread out in a bigger world. As particle densities fall, the universe should slow down rather than speed up. Space, on the other hand, stays the same as it grows. As Rees and Perlmutter's team saw, making more vacuums, which means more energy, will speed up the growth if the vacuum has its own energy. The unexpected expansion of the universe revealed a minuscule amount of energy in space known as dark energy. Luckily, Einstein thought about this option while working on general relativity. He thought that all of space might be filled with a steady amount of extra energy, represented by the symbol chi and called the cosmological constant. As matter spread out, this would prevent the universe from collapsing. Einstein was wrong about his intuition because the world doesn't balance as he thought it would. In 1998, the discovery that space was pushing everything outward led to the return of his cosmological constant, which now forms the core of the standard model of cosmology, known as the Lambda CDM model. Licia Verde, an astronomer who works with the DESI collaboration, said, "It's simple. It's one number. It has a story that you can relate to. That's why people perceive it as enduring." Now, a new group of cosmologists and telescopes may start to hear the first hints of a bigger story. Making a map of the sky. One of those telescopes is on Kitt Peak in Arizona. The DESI team has put 5,000 robotic fibers on the telescope's 4-meter mirror to automatically point at its objects in space. Unlike the Sloan Digital Sky Survey, SDSS, which required manual insertion of similar fibers into patterned metal plates, this technology enables rapid data collection. A few nights ago, DESI was able to record the locations of almost 200,000 galaxies, which set a new record. From May 2021 to June 2022, the robotic fibers sucked up photons that came from different times in the past of the universe. Since then, the DESI researchers have used that information to make the most accurate map of the universe ever. It shows the exact positions of about 6 million galaxies between 2 and 12 billion years ago in the universe's 13.8 billion year history. DESI is a great experiment producing stupendous data, Rees said. Dappled lights spread out from the middle. The magnification of one region shows a rich distribution of bright galaxies and dark voids. Earth is the center of this thin slice of DESI's 3D universe map, which, with magnification, shows the distribution of galaxies and voids. The secret to DESI's mapping accuracy is its ability to collect spectra of galaxies, data-rich plots recording the intensity of each light hue. A spectrum shows how quickly a galaxy moves away from us and, therefore, which era of cosmic history we see it in. The faster a galaxy wrecks, the older it is. That allows you to situate the galaxies relative to each other, but you need something else to calibrate the map with the right distances relative to Earth. Essential information for a full reconstruction of cosmic history. The DESI team believed that something was a patchwork of frozen density ripples left behind from the early universe. The cosmos was a hot, thick soup of mostly matter and light for the first 100,000 years after the Big Bang. Gravity pulled the matter inward while light pushed it outward, and the fight set off density ripples spreading outward from a smattering of initial dense spots in the soup. After the universe cooled and atoms formed, it became clear. Light streamed outward, leaving the ripples, baryonic acoustic oscillations, BAOs, frozen in place. The result was a collection of overlapping spheres with slightly denser shells measuring roughly 1 billion light-years across. The distance BAOs had time to travel before freezing. Those dense shells went on to form slightly more galaxies than other locations did. And when DESI researchers map millions of galaxies, they can identify traces of these spheres. Closer spheres appear larger than distant ones, but since DESI researchers know the spheres are all the same size, they can determine how far away from Earth the galaxies are and resize the map accordingly. The researchers performed a blind analysis and randomly shuffled measurements to obscure physical patterns to avoid unconsciously influencing their results. Then, the collaboration met in Hawaii last December to unscramble the results and see what sort of map the Kit Peak robotic fibers had noticed. Watching live over Zoom from his home in the United Kingdom, NARRATOR experienced a thrill when the map showed itself, as it appeared somewhat unusual. With sufficient experience with BAO data, NARRATOR understood the need for a slightly different approach from the standard model. I knew that lambda CDM wasn't quite the whole picture. Over the following week, as the researchers combed through the new dataset, analyzing it and blending it with other large cosmological datasets, they found the source of the oddness and exchanged a flurry of Slack messages. One of my colleagues posted a plot showing this dark energy constraint and didn't write any words. NARRATOR said, "It was just the plot and an exploding head emoji." DESI aims to understand how the universe has grown over time by observing different types of galaxies as they appeared during 7 epochs of cosmological history. Next, they assess the degree to which these snapshots match the expected evolution of lambda CDM. They also consider how well other theories do, such as allowing dark energy to vary between snapshots. With the first year of DESI data alone, lambda CDM fits the snapshots nearly as well as a variable dark matter model. When the collaboration combines the DESI map with other snapshots, the two ideas drift apart. Light is known as the cosmic microwave background and a series of 3 recent supernova maps. They found that the results ranged from the prediction of lambda CDM by 2.5, 3.5, or 3.9 sigmas, depending on which of the 3 supernova catalogues they included. Imagine flipping a coin 100 times. We expect a fair coin to yield 50 heads and 50 tails. If the coin yields 60 heads, it is 2 sigma away from the mean, and the probability of it happening by chance rather than coin rigging is 1 in 20. If you get 75 heads, which has a 1 in 2 million chance of happening randomly, that's a 5 sigma finding, the gold standard for claiming a discovery in physics. The sigma values found by DESI fall somewhere in between. They could be rare statistical fluctuations or real evidence that dark energy is changing. The DESI instrument has thousands of robotic fibers, allowing for dramatically faster data collection. While researchers find these numbers tantalizing, they warn against reading too much into the higher figures. The universe is much more complicated than a coin, and the statistical significance depends on subtle assumptions in the data analysis. A stronger reason for enthusiasm is that all 3 supernova catalogues, which span somewhat independent populations of supernovas, hint that dark energy is varying in the same way. Its power is waning, or as cosmologists say, thawing. When we swap out all of these complementary data sets, they all tend to converge on this slightly negative number, Brout said. If the discrepancy were random, the data sets would be more likely to point in different directions. Joshua Freeman, a cosmologist at the University of Chicago and a member of the DESI collaboration who didn't work on the data analysis, said he would be glad to see lambda CDM fall. As a theorist, He proposed theories of thawing dark energy in the 1990s, and he more recently co-founded the Dark Energy Survey, a project that searched for deviations from the Standard Model from 2013 to 2019, and created one of the 3 supernova catalogues Deci used. However, he also recalls experiencing the sting of vanishing cosmological anomalies. Freeman joked, "Until the errors get smaller, I'm not going to write my Nobel acceptance speech." Statistically speaking, it could disappear, Brout said of the difference with the Lambda CDM model. "We are now going all out to find out if it will." After wrapping up their 3rd year of observations earlier this week, the Deci researchers expect their next map to contain nearly twice as many galaxies as the one unveiled today. Now that they have more BAO analysis experience, they plan to quickly release the updated 3-year map. Next comes a 5-year map of 40 million galaxies. Beyond Deci, many new instruments are going online in the coming years, including the 8.4-meter Vera Rubin Observatory in Chile, NASA's Nancy Grace Roman Space Telescope, and the European Space Agency's Euclid mission. "Our data in cosmology has made enormous leaps over the last 25 years, and it's about to make bigger leaps," Freeman said. As they amass new observations, researchers may continue to find that dark energy appears as constant as it has for a generation. Alternatively, if the trend continues, as suggested by Deci's results, it could change everything. It could change everything. It could change new physics. If dark energy is weakening, it can't be a cosmological constant. Instead, it may be the field many cosmologists believe sparked exponential expansion during the universe's birth. This scalar field could fill space with energy that looks constant, like the cosmological constant, but eventually starts to slip over time. "The idea that dark energy is varying is very natural," said Paul Steinhardt, a cosmologist at Princeton University. "Otherwise," he added, "it would be the only form of energy we know that is absolutely constant in space and time." Should dark energy be variable, it would herald a profound paradigm shift. We would no longer inhabit a vacuum, the universe's lowest energy state, but rather an energized state, gradually sliding towards a true vacuum. As Steinhardt aptly said, "We're accustomed to perceiving our existence within a vacuum, but no one ever guaranteed that." The cosmos's fate hangs in the balance, teetering on the variability of dark energy. How quickly the number previously known as the cosmological constant declines, and how far it might go, could determine the very nature of our universe. If it reaches 0, cosmic acceleration will stop. If it dips far enough below 0, the expansion of space will turn to a slow contraction. The sort of reversal required for cyclic theories of cosmology, such as those developed by Steinhardt. String theorists share a similar outlook. Their proposal, which reduces everything to the vibration of strings, allows them to construct universes with varying dimensions and a variety of exotic particles and forces. But they can't easily construct a universe that permanently maintains stable positive energy, as our universe has seemed to. Instead, in string theory, the energy must either gently fall throughout billions of years, or violently drop to 0, or a negative value. All string theorists believe that it's one or the other. "We do not know which one," said Kumrun Vafa of Harvard University. The gentle fall scenario would benefit from observational evidence of a gradual decline in dark energy. "That would be amazing," Vafa said. "It would be the most important finding since the discovery of dark energy itself." For now, the Deci analysis is the basis for such speculations. Before seriously considering revolution, cosmologists must watch millions more galaxies. If this holds up, it could lead to a new, potentially deeper understanding of the universe, Rees said. The next few years should be very telling. Fresh X-rays show a universe as clumpy as cosmology predicts. By mapping the largest objects in the universe, cosmologists have found that a cosmic anomaly is disappearing. Launched in 2019, the eROSITA X-ray telescope has revealed a stunning revelation. It has spotted thousands of galaxy clusters across a vast swath of the cosmos, colored in this animation according to their distance from the telescope's central location. The farthest clusters emitted light 9 billion years ago, giving us a unique glimpse into our universe's past. Clusters of hundreds or thousands of galaxies sit at the intersections of giant, crisscrossing filaments of matter that form the cosmos's tapestry. Each galaxy cluster's gravity pulls everything toward its center, compressing the gas that fills the space between the galaxies, causing it to heat up and glow in X-rays. The eROSITA X-ray telescope, lofted into space in 2019, spent more than 2 years collecting pings of high-energy light from all over the sky. The data has allowed scientists to map the locations and sizes of thousands of galaxy clusters, 2/3 previously unknown. This breakthrough in mapping techniques could revolutionize our understanding of cosmic magnetism, a key yet elusive aspect of our universe. The results include new estimates of the clumpiness of the cosmos, a much-discussed characteristic of late, as other recent measurements have found it to be unexpectedly smooth, as well as masses of ghost-like particles called neutrinos, and a key property of dark energy, the mysterious repulsive energy that's speeding up the universe's expansion. Cosmologists' reigning universe model identifies dark energy as the energy of space itself and pegs it at 70% of the universe's contents. Half the universe is invisible dark matter, and 5% is ordinary matter and radiation. Under the force of gravity, everything is evolving. However, some observations from the past decade defy this standard model of cosmology, raising the possibility that the model is missing ingredients or effects that could usher in a deeper understanding. The eROSITA observations, in a remarkable display of confirmation, align with the current cosmological model on all fronts. Dragan Hutra, a cosmologist at the University of Michigan who was not involved in the work, aptly stated, "It's a remarkable confirmation of the standard model." X-raying the cosmos. After the Big Bang, subtle density variations in the newborn universe gradually became more pronounced as matter particles glommed onto each other. The denser clumps pulled in more material and grew larger. Today, galaxy clusters are the largest gravitationally bound structures in the cosmos. Determining their size and distribution lets cosmologists test their model of how the universe evolved. Abstractions guide promising ideas in science and mathematics. As you travel with us, join the discussion. To find clusters, the eROSITA team trained a computer algorithm to scour for really fluffy X-ray sources rather than point-like objects, said Ezra Bulbul of the Max Planck Institute for Extraterrestrial Physics in Garching, Germany, who led eROSITA's cluster observations. They whittled a list of candidates down to an extremely pure sample, she said, of 5,259 galaxy clusters, out of the nearly 1 million sources of X-rays the telescope detected. They then had to figure out how heavy these clusters were. Gravitational lensing is a phenomenon where massive objects bend the fabric of spacetime, changing the direction of passing light and causing the light source to appear distorted. The eROSITA scientists could calculate the masses of some of their 5,259 clusters based on the lensing of more distant galaxies sitting behind them. While only a third of their clusters had known background galaxies lined up this way, the scientists found that the cluster mass correlated strongly with the brightness of their X-rays. Because of this strong correlation, they could use brightness to estimate the masses of the remaining clusters. They then fed the mass information into computer models of the evolving cosmos to infer the values of cosmic parameters. One interesting number is the universe's clumpiness factor, S8. An S8 zero value would represent a vast cosmic nothingness akin to a flat plane with a rock in sight. An S8 value closer to 1 corresponds to steep mountains looming over deep valleys. Scientists have estimated S8 based on cosmic microwave background measurements, CMB, ancient light from the early universe. Extrapolating from the cosmos's initial density variations, Researchers expect the current S8 value to be 0.83. However, recent studies looking at galaxies today have measured values 8% to 10% lower, implying that the universe is unexpectedly smooth. That discrepancy has intrigued cosmologists, possibly pointing to cracks in the standard cosmological model. Red and blue dots of various sizes decorate an image of the sky. The Milky Way forms a band across the center. Here we plot the eROSITA catalogue of galaxy clusters on a half-sky map. The colors indicate the cluster's distance, and the circle's sizes show the apparent X-ray brightness of each source. The eROSITA team, however, found no such discrepancy. Our result was basically in line with the prediction from a very early time, from the CMB, said Vittorio Ghirardini, who led the analysis. He and his colleagues calculated an S8 value of 0.85. Ghirardini said some team members were disappointed since hinting at missing ingredients was a more exciting possibility than matching the known theory. The S8 value sitting a tad higher than the CMB estimate will likely trigger more analysis from other teams, said Gerrit Schellenberger, an astrophysicist who studies galaxy clusters at the Harvard-Smithsonian Center for Astrophysics. I believe it's probably not the last paper we have seen on that topic. According to Marilena Loverde, a cosmologist at the University of Washington, neutrinos formed in the early universe, nearly as many as photons, particles of light. But physicists know neutrinos, unlike photons, must have tiny masses because they oscillate between three types. The particles don't acquire mass through the same mechanism as other elementary particles, so their mass is a much-studied mystery. And the first question is how massive they actually are. The nature of dark energy is the biggest question that cosmology has. Cosmologists can estimate neutrinos' mass by studying their effects on the cosmos's structure. Neutrinos zip around at nearly the speed of light and pass right through other matter rather than glomming onto it, so their presence in the cosmos has attenuated its clumpiness. The more mass you put on neutrinos, the more of the mass that is smooth on those large scales, Loverde said. Combining their galaxy cluster measurements with CMB measurements, the eROSITA team estimated that the sum of the masses of the three types of neutrinos is no more than 0.1 electron volts, eV, or less than a millionth of the mass of an electron. Other neutrino experiments have established a lower bound, showing that the three neutrino masses must add up to at least 0.06 eV for one possible ordering of the three mass values, or 0.1 eV for the inverted order. As the distance between the upper and lower bounds decreases, scientists are getting closer to pinpointing the neutrino mass value. We are actually on the brink of making a breakthrough, Bulbul said. In subsequent data releases, the eROSITA team could sufficiently push down the upper bound to rule out the inverted order neutrino mass models. Caution is advised. Any other speedy, lightweight particles that might exist, such as axions or hypothetical particles suggested as candidates for dark matter, would have the same effects on structure formation and introduce errors in neutrino mass measurement. Measurements of galaxy clusters can show how structures grew and how dark energy, the thin coating of repulsive energy that permeates space, accelerates its expansion, and thereby separates matter, impeded their growth. The standard model of cosmology assumes that dark energy is the energy of space itself, which is why it maintains a constant density throughout space and time, often referred to as the cosmological constant. But if its density drops over time, then it's something entirely different. That's the biggest question that cosmology has, said Sebastian Grandis, an eROSITA team member at the University of Innsbruck in Austria. According to the researchers' map of thousands of clusters, dark energy fits the profile of a cosmological constant, although their measurement has a 10% uncertainty, so an ever so slightly varying dark energy density remains possible. Originally, eROSITA, which sits aboard a Russian spacecraft, was to conduct 8 full-sky surveys. But in February 2022, weeks after the telescope began its 5th survey, Russia invaded Ukraine. In response, the German side of the collaboration, which operates and runs eRosita, put the telescope into safe mode, ceasing all scientific observations. These initial papers draw from just the first 6 months of data. In the additional 1.5 years of observations, the German group anticipates finding about 4 times as many galaxy clusters, enabling more accurate pinpointing of all these cosmological parameters. Cluster cosmology could be the most sensitive probe of cosmology other than the CMB, said Anja von der Linden, an astrophysicist at Stony Brook University. Their initial results show the power of a relatively untapped information source. Grandis acknowledged that they are relatively new to the field. Radio maps may show the universe's biggest magnetic fields. A controversial technique has produced detailed maps of the magnetic fields in colossal galaxy clusters. Confirming this approach could reveal the origin of cosmic magnetic fields. The image of the El Gordo galaxy cluster superimposes blue magnetic field lines on hundreds of galaxies. The magnetic field is swirly and resembles a fingerprint. Using radio waves, astronomers mapped the magnetic field within the 6 million light-year-long El Gordo cluster of galaxies. By making maps of the magnetic fields hidden inside massive galaxy clusters, astronomers are getting closer to finding the origin of cosmic magnetism. These are the first maps of the detailed structure of magnetic fields on an unprecedentedly large scale, said Alexandra Lazarian, an astronomer at the University of Wisconsin-Madison, and a co-author on the paper describing the maps, published today in Nature Communications. Lazarian and his colleagues studied 5 galaxy clusters spanning millions of light-years. They made the maps using a technique he devised called synchrotron intensity gradient, SIG mapping, which relies on radio observations to determine which way a cluster's magnetic field points at a given location. By applying the same technique across an entire cluster, the researchers say they can construct a complete map of its magnetic fields. The results, if confirmed, would show that there's a previously undetected order to magnetic fields in giant structures. Abstractions guide promising ideas in science and mathematics. As you travel with us, join the discussion. Magnetism is ubiquitous in the universe. We see it from the smallest scales on Earth to the universe's largest, where it sculpts cosmic structures such as stars and the interstellar medium. Magnetism is also crucial for life as we know it, influencing chirality at a molecular level and crafting the protective shield that encompasses Earth. However, there is one big, unanswered question about where cosmic magnetism originated. Some scientists favor a primordial explanation, with magnetism arising in the first moments after the Big Bang and other fundamental forces. Others favor a later arrival, with magnetism arising after hundreds of millions of years and growing from seed magnetic fields produced by objects such as stars and galaxies. This new mapping technique might offer a solution by allowing astronomers to compare magnetic fields on the largest scale. However, the technique has its own limitations and remains controversial in the field of large-scale magnetism. If it works, it gives you a very observationally inexpensive way of mapping magnetic fields over very large areas of the sky, said Kate Pattle, an astrophysicist at University College London. Typically, scientists discover cosmic magnetic fields by examining synchrotron radiation, which results from a magnetic field's ability to bend the path of electrons traveling at near light speed. Such observations can also use the orientation of those radio emissions, their polarization, to reveal the orientation of the magnetic fields. However, polarization measurements are extremely time-consuming and work best in a galaxy cluster's denser and dustier regions, About 7 years ago, Lazarian developed a method that used synchrotron emission alone to reveal the direction of the magnetic field. No polarization was required. The technique relies on observations of the radio emission's changing strength as you move across space, or what researchers call the gradient. The gradient in the brightness, The direction in which the image becomes fainter or brighter relates to the magnetic fields, said Markus Bruggen, a professor of astrophysics at the University of Hamburg in Germany, who has previously studied large magnetic fields. In preliminary observations of interstellar space, everywhere we looked, we revealed this magnetic field structure, Lazarian said. The team then turned to galaxy clusters, which grow as smaller groups of galaxies collide. When these mergers occur, they produce shock fronts that plow through the intracluster medium, Bruggen said. Magnetic fields interact with those turbulent shock fronts and produce synchrotron emission. By observing the gradient of that emission, the researchers can infer the direction of the magnetic field, which in turn reflects the mergers that have built these clusters over time. The method allows Lazarian to survey magnetic fields across large galaxy clusters, including the diffuse intergalactic space within the structure where polarization measurements are impossible. To make their maps, the team targeted 5 galaxy clusters, including El Gordo, a well-studied clump of hundreds of galaxies that stretches 6 million light-years across. They also looked at Abell 2345, 2 billion light-years away, Abell 3376, about 500 million light-years away, and 2 others. However, not all scientists are convinced that the strategy accurately tracks the motion of magnetic fields. Changes in electron or gas density could cause shifts in magnetism-driven synchrotron gradients. The method also relies on a phenomenon known as turbulence in galaxy clusters, where magnetic fields twist and turn together. A notoriously complex physical process, said Andrea Bottian, an astrophysicist at the National Institute for Astrophysics in Italy. Lazarian plans to use SIG, if the technique holds up, to map the magnetism in filaments between galaxies using a vast European radio network called the Low Frequency Array. If the fields in those filaments align with each other, as they do in clusters, it could indicate a primordial origin of the cosmic magnetic structure instead of a gradual emergence from seed magnetic fields. Such an alignment would be essentially impossible for stars and galaxies to create during later cosmic epochs, Bruggen said. I believe we will discover the production of magnetic fields early in the universe, Bruggen stated. Divining the origin of magnetism may tell us something about the cosmos's habitability. Life itself, at least as we know it on Earth, relies on magnetism and its influence on chirality to give the building blocks of life a right or left-handedness. If magnetic fields formed at the beginning of the universe, you could form molecules with chirality very early, Lazarian said. Then, we can ask the question of whether we should expect to see signals of civilizations that formed quite early in the history of the universe. He also noted that magnetic fields in galaxy clusters could be the source of some of the highest energy cosmic rays known to pervade the universe, which still have a mysterious origin. There's a big question about whether these clusters of galaxies could be the sources of the cosmic rays of the highest energy, he said, and mapping the fields within clusters could help resolve that question. The team's next goal is to observe galaxy clusters farther away and further back in time. El Gordo, although immense, only stretches back to when the universe was 6.5 billion light-years old, about half its current age of 13.8 billion years. Future radio telescopes, like the Square Kilometre Array, a vast array of antennas spanning 1 million square meters in South Africa and Australia later this decade, have the potential to apply this type of mapping to clusters that existed as early as 3 billion years ago. I would like to see what happened in the early universe, said Yue Hu, a graduate student at the University of Wisconsin-Madison and the paper's lead author. However, this method is the first step towards understanding the origin of magnetism in the universe and all its implications. It's one piece of the puzzle, Bruggen said, but it's a very substantial piece. In a dark dimension, physicists search for the universe's missing matter. String theory suggests that dark matter hides in a relatively large extra dimension. The theory makes testable predictions that physicists are investigating now. An illustration. A large, dark, spherical space is filled with many smaller spheres of varying sizes. In the background are multiple stars and galaxies. In a dark extra dimension, peculiar particles convey the gravitational force. When understanding the fabric of the universe, most of what scientists believe exists falls into a murky, dark realm. Ordinary matter, the stuff we can see and touch, accounts for just 5% of the cosmos. The rest, cosmologists say, is dark energy and matter, mysterious substances labeled dark, partly to reflect our ignorance about their true nature. Only a few ideas introduced 2 years ago have the potential to explain everything we hope to know about the cosmos and answer some important questions. The dark dimension scenario offers a specific recipe for dark matter and suggests an intimate connection between dark matter and energy. The scenario might also tell us why gravity, which sculpts the universe on the largest scales, is so weak compared to the other forces. The scenario proposes an as-yet unseen dimension within the already complex realm of string theory, which attempts to unify quantum mechanics and Einstein's theory of gravity. In addition to the 4 familiar dimensions, 3 infinitely large spatial dimensions plus 1 of time, string theory suggests 6 exceedingly tiny spatial dimensions. One of those dimensions is significantly larger than the others in the dark dimensions universe. Instead of being 100 million trillion times smaller than a proton's diameter, it measures about 1 micron across, minute by everyday standards, but enormous compared to the others. This dark dimension generates massive particles that carry the gravitational force, forming the dark matter that scientists believe accounts for about 25% of our universe, and is the glue that holds galaxies together. Current estimates hold that the remaining 70% is dark energy, driving the universe's expansion. The scenario allows us to make connections between string theory, quantum gravity, particle physics, and cosmology, while addressing some of the mysteries related to them, said Ignatios Antoniadis, a physicist at Sorbonne University, who is actively investigating the dark dimension proposal. While there's no evidence yet that the dark dimension exists, the scenario makes testable predictions for cosmological observations and tabletop physics. This implies that we might not have to wait long to discover if the hypothesis can withstand empirical scrutiny, or if it falls into the category of intriguing concepts that never realized their initial potential. Physicist Rajesh Gopakumar, the director of the International Center for Theoretical Sciences in Bengaluru, said, "We envision the dark dimension here. As upcoming experiments become more precise, they could easily eliminate it." Divining the dark dimension. Albert Einstein's introduction of the Greek letter lambda, a term representing the cosmological constant, into his gravity equations in 1917, was pivotal. Inspired by his belief in a static universe, Albert Einstein intended this act to prevent the equations from describing an expanding universe, a view that many of his contemporaries shared. However, in the 1920s, astronomers made a groundbreaking discovery. The universe was indeed expanding. This was further confirmed in 1998, when they observed that the expansion was accelerating, driven by what we now know as dark energy, a term that can also be represented by a lambda in equations. Since then, scientists have been intrigued by a unique feature of lambda, its estimated value of 10 to the 122 in Planck units, which is considered the smallest measured parameter in physics, according to Kumrun Vafa, a physicist at Harvard University. While contemplating this almost unfathomable smallness with his research team in 2022, Vafa had a revelation. Such a minuscule lambda is an extreme parameter, a characteristic he could explore within the framework of his previous work in string theory. Vafa and his colleagues had previously formulated a conjecture that sheds light on what happens when a significant physical parameter assumes an extreme value. This conjecture, known as the distance conjecture, refers to distance in an abstract sense. When a parameter moves towards the remote edge of possibility, thereby assuming an extreme value, it will have implications for the other parameters. Thus, the equations of string theory do not fix key values such as particle masses, lambda, or the coupling constants that dictate the strength of interactions. Altering one will inevitably affect the others. For instance, as observed, much lighter, weakly interacting particles with masses directly related to the lambda's value should accompany an extraordinarily small lambda. What could they be? Vafa wondered. As he and his colleagues pondered that question, they realized that the distance conjecture and string theory combined to provide one more key insight. For these lightweight particles to appear when lambda is nearly zero, one of string theory's extra dimensions must be significantly larger than the others, perhaps large enough for us to detect their presence and even measure them. They had arrived in the dark dimension, the dark tower. To understand the genesis of the inferred light particles, we need to rewind cosmological history to the first microsecond after the Big Bang. At this time, the cosmos was dominated by radiation, specifically photons and other particles traveling at speeds close to light. The standard model of particle physics already describes these particles. But in the dark dimension scenario, a family of particles that are not part of the standard model can emerge when the familiar ones collide. Every now and then these radiation particles collided with each other, creating what we call dark gravitons, said Georges Aubier, a physicist at the University of Oxford who helped craft the theory of dark gravitons. There is one massless graviton, the usual graviton, and infinitely many copies of dark gravitons, all of which are massive. Normally, physicists define gravitons as massless particles that travel at the speed of light and convey the gravitational force, similar to the massless photons that convey the electromagnetic force. However, in this scenario, as Aubier explained, these early collisions created a different type of graviton, something with mass. More than that, they produced a range of different gravitons. There is one massless graviton, which is the normal graviton we know, Aubier said, and then there are infinitely many copies of dark gravitons, all of which are massive. The masses of the postulated dark gravitons are, roughly speaking, an integer times a constant, m, whose value is tied to the cosmological constant, and there's a whole tower of them with a broad range of masses and energy levels. To understand how this all might work, imagine our four-dimensional world as the surface of a sphere. We can never leave that surface, for better or worse, and that's true for every particle in the standard model. Gravitons, on the other hand, can travel everywhere because gravity exists. And that's where the dark dimension comes in. A portrait of Georges Aubier. He's wearing a plaid shirt and smiling. Georges Aubier and his colleagues discovered how colliding particles may have produced dark gravitons in the first microseconds after the Big Bang. To picture that dimension, Vafa said, think of every point on the imagined surface of our four-dimensional world and attach a small loop to it. That loop is the extra dimension, at least schematically. If two standard model particles collide and create a graviton, the graviton can leak into that extra dimensional circle and travel around it like a wave, Vafa said. Quantum mechanics tells us that every particle, including gravitons and photons, can behave like a particle and a wave, a 100-year-old concept known as wave-particle duality. As gravitons leak into the dark dimension, their waves can have different frequencies, each corresponding to different energy levels. Those massive gravitons traveling around the extra-dimensional loop produce a significant gravitational influence at the point where the loop attaches to the sphere. Could this be the key to understanding dark matter? The gravitons we have postulated are weakly interacting yet capable of mustering some gravitational heft. This idea's merit lies in the fact that gravitons, initially proposed as carriers of the gravitational force, have been a part of physics for 90 years. We have not directly detected gravitons, as they are hypothetical particles. But to explain dark matter, we don't have to introduce a new particle, as Vafa pointed out. This could revolutionize our understanding of the universe. You can only test or prove me right if I show you some correlation. Predicting something that you can prove or disprove is much more interesting. Gravitons that can leak into the extra-dimensional domain are natural candidates for dark matter, said Georgi Dvali, director of the Max Planck Institute for Physics, who is not working directly on the dark dimension idea. A large dimension, such as the posited dark dimension, would have room for long wavelengths which imply low-frequency, low-energy, low-mass particles. But if a dark graviton leaked into one of string theory's tiny dimensions, its wavelength would be exceedingly short, and its mass and energy would be very high. Supermassive particles like this would be unstable and very short-lived. They would be long gone, Dvali said, without having the possibility of serving as dark matter in the present universe. Gravity and its carriers, gravitons, permeate all the dimensions of string theory. However, the dark dimension is significantly larger, by many orders of magnitude, than the other extra dimensions, diluting the strength of gravity and making it appear weaker in our four-dimensional world if it were to penetrate significantly into the larger dark dimension. Dvali noted that other extra-dimensional scenarios would also exhibit this effect. We can empirically test the dark dimension scenario because it can predict things like dark matter. If I give you some correlation, you can never test, you can never prove me wrong, said Valenzuela, a co-author of the original Dark Dimension paper. It's much more interesting to predict something that you can actually prove or disprove. Astronomers have known dark matter existed, at least in some form, since 1978, when the astronomer Vera Rubin discovered that galaxies were rotating so fast that stars on their outermost fringes would be cast off into the distance if not for vast reservoirs of some unseen substance holding them back. Identifying that substance, however, has proved very difficult. Experimental efforts to detect dark matter for nearly 40 years have yielded no such particle. Vafa said that if the dark matter turns out to be dark gravitons, which are exceedingly weakly interacting, that won't change. They will never be found directly. However, there may be opportunities to indirectly spot those graviton signatures. Vafa and his collaborators are pursuing a strategy based on large-scale cosmological surveys that chart the distribution of galaxies and matter. In those distributions, small differences in clustering behavior, Obeid said, might signal the presence of dark gravitons. When heavier dark gravitons decay, they produce a pair of lighter dark gravitons with a combined mass slightly less than that of their parent particle. Einstein's formula, E=mc2, converts the missing mass into kinetic energy, giving the newly created gravitons a slight boost, a kick velocity, estimated to be about 1/10 of the speed of light. These kick velocities, in turn, could affect how galaxies form. According to the standard cosmological model, galaxies start with a clump of matter whose gravitational pull attracts more matter. However, gravitons with sufficient kick velocity can escape this gravitational grip. If they do, the resulting galaxy will be slightly less massive than the standard cosmological model predicts. Astronomers can investigate this difference. Theorists are always trying to do this by tying together. The dark dimension is one of the most promising ideas I've heard. Rajesh Gopakumar, International Center for Theoretical Science. Recent observations of cosmic structure from the Kilo Degree Survey are consistent with the dark dimension. The survey's data analysis placed an upper bound on the kick velocity, which was very close to the value Obeid and his co-authors predicted. The Euclid Space Telescope, launched last July, will provide a more stringent test. Meanwhile, physicists plan to test the dark dimension concept in a laboratory setting. If gravity leaks into a dark dimension measuring 1 micron across, one could look for deviations from the expected gravitational force between two objects separated by that distance. It's not an easy experiment to carry out, said Armin Shayegi, a physicist at the Austrian Academy of Sciences conducting the test. But there's a simple reason for why we have to do this experiment, he added. We won't know how gravity behaves at such close distances until we look. The closest measurement to date, carried out in 2020 at the University of Washington, involved a 52-micron separation between two test bodies. The Austrian group aims to achieve the predicted 1-micron range for the dark dimension. While physicists find the dark dimension proposal intriguing, some are skeptical that it will work out. Searching for extra dimensions through more precise experiments is a very interesting thing to do, said Juan Maldacena, a physicist at the Institute for Advanced Study, though I think that the probability of finding them is low. Joseph Conlon, a physicist at Oxford, shares that skepticism. There are many ideas that would be important if true, but are probably not. Here's one of them. The conjectures it is based on are somewhat ambitious, and I think the current evidence for them is rather weak. Of course, the weight of the evidence can change, which is why we do experiments in the first place. If validated by upcoming tests, the dark dimension proposal could advance our understanding of dark matter, its connection to dark energy and gravity's apparent weakness compared to other known forces. Theorists are always trying to do this, tying together. The dark dimension is one of the most promising ideas I have heard in this direction, Gopakumar said. But in an ironic twist, the one thing the dark dimension hypothesis cannot explain is why the cosmological constant is so staggeringly small, a puzzling fact that essentially initiated this whole line of inquiry. It's true that this program does not explain that fact, Waffer admitted. However, based on this scenario, we can infer that many remarkable events could occur if the lambda is small and the consequences are clearly defined. Cosmologists employ a small set of numerical values and parameters to describe and define our universe. The values mentioned here represent tangible objects, specifically gears, within a vast cosmic apparatus, with each component intricately linked to one another. One of those parameters relates to the degree of mass aggregation. This sheds light on how dark energy functions, as its outward acceleration force defies the gravitational pull of cosmic mass. Scientists utilize a parameter known as S8 to measure the degree of clumpiness. According to Sunao Sugiyama, an observational cosmologist at the University of Pennsylvania, the universe lacks any variation or structure if the value is 0. The terrain resembles a level and barren grassland devoid of any anthills that would disrupt the uniformity of the scenery. However, when the value of S8 approaches 1, the universe resembles an expansive and rugged mountain range characterized by substantial clusters of dense matter interspersed with vast empty spaces. The Planck spacecraft's observations of the primordial universe, during which the initial seeds of the cosmic structure formed, yielded a value of 0.83. Sunao Sugiyama of the University of Pennsylvania's analysis suggests that theories may not accurately predict the distribution of matter in the cosmos. Scientists conduct extensive surveys of vast regions of the sky to compare the level of clustering in the present-day universe with measurements taken during the early stages of the universe's existence. Quantifying the presence of observable galaxies is a separate matter. However, a separate challenge lies in accurately charting the imperceptible network on which those galaxies reside. To accomplish this, cosmologists analyze the minute distortions in the light emitted by galaxies caused by the gravitational influence of undetectable matter that bends the path of light as it travels through the universe. By examining these distortions, known as weak gravitational lensing, scientists can map out the arrangement of dark matter along the trajectories of light and approximate the locations of galaxies. Astronomers utilize both pieces of data to construct three-dimensional maps of the visible and invisible mass in the universe. This enables them to quantify the evolution and expansion of the cosmic structure. In recent years, 3 surveys utilizing weak lensing techniques have successfully mapped extensive sky regions. The Dark Energy Survey, DES, which utilizes a telescope in Chile's Atacama Desert. The Kilo Degree Survey, KIDS, also in Chile. And the Hyper-Suprime CAM, HSC, of the Subaru Telescope in Hawaii, which conducts a 5-year survey, are among these surveys. In recent years, the DES and KIDS surveys yielded S8 values lower than those obtained by Planck. This suggests that the mountain ranges formed from the primordial cosmic soup had smaller peaks. However, those hints provided alluring indications of imperfections in our understanding of cosmic structures' growth and aggregation. Cosmologists eagerly awaited the release of the Subaru HSC results in December, as they needed more data. The Subaru HSC team surveyed tens of millions of galaxies, covering an area of approximately 416 square degrees in the sky. This area is equivalent to the size of 2,000 full moons. In their specific region of the sky, the team determined an S8 value of 0.78, which is smaller than the value the Planck telescope obtained when observing the radiation of the early universe. This result is consistent with the initial findings of previous surveys. The Subaru team acknowledges that their measurements provide only a preliminary indication of tension, as they have yet to achieve the statistical significance required by scientists. However, they are actively working to extend their data by an additional 3 years of observations. If the existence of this S8 tension is indeed accurate, there is still an aspect that eludes our comprehension, stated Sugiyama, who spearheaded one of the Subaru HSC analyses. Cosmologists are currently examining the specific details of the observations to identify any sources of uncertainty. The Subaru team approximated the distances to the majority of their galaxies by considering their overall color, a method that may result in inaccuracies. Incorrect estimation of the average distance would lead to inaccurate determination of certain cosmological parameters that are of significance, stated Rachel Mandelbaum, a Carnegie Mellon University team member. Indeed, there may be several instances of novel physics in action. Obtaining these measurements poses challenges and requires careful interpretation due to their intricate nuances. Diana Scognamiglio from NASA's Jet Propulsion Laboratory stated that the distinction between a galaxy's distorted appearance and its true shape, which is crucial for detecting hidden mass, is typically minimal. Furthermore, Earth's atmosphere can slightly alter a galaxy's appearance through distortion. This is one of the reasons Scognamiglio conducted a weak lensing analysis on NASA's James Webb Space Telescope. Recently, scientists from the DES and KIDS teams have reanalyzed their measurements and obtained an S8 value that aligns more closely with the results obtained from the Planck experiment, thereby introducing further complexity. The Hubble tension, a discrepancy between the current measurements of the universe's expansion rate and the value obtained from the early universe, is a topic of intense investigation. Some cosmologists are exploring whether the different S8 measurements are conflicting. As Hill stated, no clear indication of a significant and disastrous failure exists. However, he added, it is not unlikely that something intriguing might occur, hinting at the potential implications and excitement surrounding this area of research. Where cracks are visible. Scientists initially observed discrepancies in measurements of another cosmological parameter a dozen years ago. However, it took several years to gather sufficient data to persuade the majority of cosmologists that they were facing a significant and urgent problem. To summarize, the current measurements of the rate at which the universe is expanding, also known as the Hubble constant, do not align with the value obtained by extrapolating from the early universe. The perplexing situation has been dubbed Hubble tension. Astronomers must know the precise distances of celestial objects to determine the Hubble constant. Scientists near the cosmos use stars known as Cepheid variables to determine distances, which exhibit periodic brightness fluctuations. A widely recognized correlation exists between the rate at which one of these stars oscillates from its highest to lowest brightness and the energy it emits. Astronomers discovered this correlation in the early 20th century, allowing them to compute a star's inherent luminosity and determine its distance by contrasting it with its observable brightness. By utilizing these variable stars, scientists can accurately determine the distances to galaxies as far as 100 million light-years from our location. However, to observe objects located at a greater distance and existing in the past, scientists rely on a more luminous reference point, a particular kind of stellar explosion known as a type Ia supernova. Astronomers can determine the intrinsic luminosity of these standard candles, enabling them to accurately measure distances to galaxies that are billions of light-years away. These observations have assisted astronomers in determining the rate at which the universe nearby is expanding, which is approximately 73 kilometers per second per megaparsec over the last 20 years. As the distance increases by 1 megaparsec, equivalent to 3.26 million light-years, the rate at which space is receding increases by 73 kilometers per second. If the expansion rate escalates, we can temporarily alleviate the Hubble tension in the early universe. Nevertheless, that value contradicts the one obtained from another ruler integrated into the infant universe. Initially, the universe consisted of extremely hot plasma, a mixture of basic particles and energy. According to Vivian Poulin-Détol, a cosmologist from the University of Montpellier, the situation was chaotic. In the very short history of the universe, there was an event that sent sudden changes through the dense plasma in the form of pressure waves. This event may have been a phase of rapid expansion known as inflation. The universe's cooling eventually liberated the light, previously confined within the elemental plasma fog. Poulin-Détol asserts that we can observe early pressure waves through the cosmic microwave background, CMB, a form of light. This is similar to how the surface of a frozen lake preserves the patterns of overlapping waves. Cosmologists have quantified the predominant wavelength of the frozen pressure waves and utilized it to compute a value for the Hubble constant, which is 67.6 kilometers s/MPC, with an uncertainty of less than 1%. The significantly incongruous values of approximately 67 and 73 have ignited a fervent and ongoing dispute within the field of cosmology. Astronomers use autonomous celestial distance indicators. Over the last 6 years, Wendy Friedman from the University of Chicago, who has dedicated 25 years to studying the Hubble constant, has concentrated on a specific category of ancient red stars commonly found in galaxies' outer regions. Reducing the number of overlapping luminous stars and decreasing dust can result in more precise measurements. Friedman and her colleagues used these stars to determine an expansion rate of approximately 70 kilometers s/MPC, which exhibits a favorable level of concordance with the Cepheids, as Friedman stated. However, it also exhibits a high level of concordance with the microwave background. She has employed JWST's high-powered infrared sensor to address the problem. She and her colleagues are measuring the distances to these massive red stars in 11 neighboring galaxies. Simultaneously, they also measure the distances to Cepheids and a specific type of pulsating carbon star in those same galaxies. We anticipate publishing the results during the spring season. However, the researcher has already expressed that the data appears exceptionally impressive. Hill, who is working to understand the complexities of universal models, said, "I am highly intrigued to witness their discoveries. Will these recent observations exacerbate the discrepancies in cosmology's most widely accepted model? Is there a new model?" Scientists attempt to incorporate the data into their most accurate universe models, as observations limit these essential cosmological parameters. By using more accurate measurements, they could resolve their issues or attribute the tensions to ordinary factors like the idiosyncrasies of their instruments. The models may be inaccurate, which requires the creation of new ideas or theories, referred to as new physics. According to Hill, either our current models lack the necessary sophistication to accurately explain everything, or there could be multiple components of new physics influencing the situation. What could they be? Hill proposed the potential existence of a new fundamental force field, undiscovered interactions between dark matter particles, or novel components that our current understanding of the universe still needs to account for. New physics models modify the concept of dark energy by introducing a sudden increase in cosmic acceleration during the early stages of the universe, before the formation of electrons and protons. Mark Kamionkowski, a cosmologist at Johns Hopkins University, stated that a marginal augmentation in the expansion rate during the universe's early stages could address the Hubble tension. In 2016, Kamionkowski and one of his graduate students introduced the concept, and 2 years later, they delineated specific indicators that a cosmic microwave background telescope with high resolution should be capable of detecting. The Atacama Cosmology Telescope, situated atop a mountain in Chile, detected some of those signals. Nevertheless, subsequent scientists have demonstrated that the model has encountered issues with additional cosmic measurements since then. According to Dragan Huterer, a theoretical cosmologist at the University of Michigan, explaining the phenomenon where an extra form of dark energy briefly intensifies and then diminishes is too complex. Alternative solutions to the Hubble tension exhibit an even greater discrepancy when compared to observations. He described them as hopelessly tuned, resembling just-so stories that are excessively specific and not aligned with the notion that simpler theories tend to prevail over complex ones. The incoming data expected next year has the potential to be beneficial. Initially, Friedman's team will scrutinize the results of various investigations of the neighboring expansion rate. In April, researchers will unveil the initial findings from the Dark Energy Spectroscopic Instrument, the most extensive cosmological sky survey to date. The Atacama Cosmology Telescope team and researchers using the South Pole Telescope will soon publish their detailed findings on the microwave background, creating another primordial background map. The European Space Agency's Euclid, a space telescope launched in July, and the Vera C. Rubin Observatory, an all-sky mapping machine built in Chile that will be fully operational in 2025, will provide observations on the more distant horizon. Estimates place the universe's age at approximately 13.8 billion years. However, our efforts to comprehend it and our position within it are still at an early stage. We achieved cosmology's coherence 15 years ago during a fleeting calm period that ultimately proved illusory. The fissures that emerged 10 years ago have expanded significantly, resulting in larger divisions within cosmology's preferred model. Now, Di Valentino declared, the entire landscape has undergone a profound transformation. The cosmic void surrounds our galactic neighborhood like a vibrant city in a desolate desert. This vast expanse of space is incredibly empty and difficult to comprehend. Recently, sky surveys have detected a multitude of additional empty bubbles. Currently, scientists have discovered a method to extract data from these vast regions of space devoid of matter, known as cosmic voids. Scientists have developed a novel method to investigate two of the most challenging questions in cosmology by quantifying the number of entities present within a given volume of space. This is the inaugural instance in which we have employed void numbers to derive cosmological insights, stated Alice Pisani, a cosmologist at Princeton University and the Flatiron Institute, who authorized a recent preprint detailing the research. We must strive to exceed the limits of scientific exploration that we have already achieved. Scientists are actively seeking novel instruments, primarily because significant enigmas require resolution. The primary and most puzzling aspect is the pace at which the universe expands, quantified as the Hubble constant. Scientists have grappled with conflicting measurements of this rate for more than 10 years, some even referring to the problem as the most significant crisis in cosmology. Furthermore, scientists have contradictory data regarding the clumpiness of cosmic matter, which refers to the average density of various components, such as large-scale structures, dark matter, galaxies, gas, and voids spread across the universe over time. Astronomers usually quantify those values using two complementary methods. These two methods yield distinct values for the Hubble constant and the matter clustering strength. In their novel methodology, Pisani and her colleagues calculate both values using cosmic voids. The initial findings, which align more closely with one of the conventional approaches than the other, add further intricacies to an already tense dispute. In this photograph, Alice Pisani smiles towards the camera. The presence of her teal shirt makes the background indistinct and less defined. Alice Pisani, a Princeton University cosmologist, is optimistic that cosmic voids will answer some of the enduring enigmas in cosmology. The Hubble tension has persisted for a decade due to its inherent difficulty, stated Adam Rees, an astronomer at Johns Hopkins University, who employs supernovas to calculate the Hubble constant. After examining the apparent problems and enhancing the data, we have found that the predicament persists and becomes more complex. Voids are spatial regions with a lower average density than the rest of the universe. Their immense sheets and filaments delineate the vast expanse of galaxies spread across the universe. Certain regions of space, known as voids, can extend over vast distances of hundreds of millions of light-years. Collectively, these expansive regions constitute a minimum of 80% of the total volume of the universe. Nevertheless, individuals ought to have devoted greater scrutiny to them over an extended period. I initiated my research in 2011, examining approximately 200 voids, Pisani stated. However, at present we have approximately 6,000. Bubbles expand because there is no significant matter within them, resulting in a lack of inward gravitational force. As a result, the surrounding matter tends to remain distant from the bubbles. Galaxies initially located within the void move outward due to the gravitational pull of the structures outlining their boundary. Consequently, voids are characterized by a need for significant astrophysical events, such as mergers or complex phenomena. This simplicity renders voids highly manageable and straightforward to study. Nevertheless, the shape of each void varies, posing a challenge for scientists in their efforts to distinguish them. We aim to ensure that our voids are strong and resilient, Pisani stated. What is the minimum level of emptiness required, and what method should I use to quantify it? The definition of nothing varies depending on the specific information that astronomers seek to extract. Pisani and his colleagues initially employed a Voronoi diagram, a mathematical tool for identifying the shapes that make up a 3D mosaic. These diagrams commonly analyze phenomena such as bubbles in foam and cells in biological tissues. As part of the Baryon Oscillation Spectroscopic Survey, BOSS, a large-scale project to map the galaxy, Pisani and her colleagues used Voronoi tessellations to find about 6,000 empty regions. Voids enhance the catalogue of galaxies, stated Benjamin Wandelt, an astrophysicist at Sorbonne University in Paris, who was not involved in the research. These are novel methods for investigating the structure of the universe. After obtaining their map of voids, Pisani and colleagues embarked on an investigation to uncover the insights it could provide regarding the universe's expansion. Creation from non-existence. Each cosmic void serves as a gateway to a significant cosmic battle. Dark energy, an enigmatic force responsible for the accelerating expansion of our universe, represents one faction. Dark energy exerts its dominance even in empty regions of space. On the other side, gravity strives to bring the voids together. As matter becomes more concentrated, it generates irregularities within the voids. Pisani, her colleagues, and Sofia Contarini from the University of Bologna conducted a study to simulate the impact of the universe's expansion on the number of voids of varying sizes. Adjusting the expansion rate while keeping other cosmological factors constant showed that a slower expansion resulted in a greater abundance of smaller, more irregular voids. Conversely, a faster expansion rate and reduced clumping of matter would increase the presence of larger, smoother voids. Subsequently, the group juxtaposed their model projections with data from the BOSS survey, enabling them to ascertain the density irregularities and the Hubble constant. At the Kavli Institute for Theoretical Physics in Santa Barbara, California, Cosmologists Wendy Friedman and Adam Rees recently debated the universe's expansion rate. They then compared their measurements with the two conventional methodologies for quantifying these quantities. The initial approach entails utilizing a form of celestial detonation called a Type Ia supernova. The second approach depends on the cosmic microwave background, CMB, the radiation from the universe's inception known as the Big Bang. The void data analysis revealed a less than 1% difference in the Hubble constant from the cosmic microwave background, CMB estimate. The findings regarding the clumpiness were less clear, but they still showed a stronger agreement with the CMB compared to Type Ia supernovas. Interestingly, the BOSS survey observed voids closer to recent Type Ia supernovas, which somewhat unexpectedly aligns the void measurements more closely with the primordial cosmic microwave background, CMB. Wandelt, however, proposed that these findings could lead to a novel comprehension of the universe. "There is one profound revelation that gives me goosebumps," he stated. "Voids do not fill empty spaces or create structures within them. They are simply voids. If the laws of physics in the early universe differed from today's, the voids might have retained evidence. The prospects of non-existence." Some believe it is premature to make definitive judgments based on the recent findings. Despite numerous gaps in the data, the study's error bars still need to be narrower to draw any definitive conclusions. Ruth Durrer, a theoretical physicist at the University of Geneva who was not involved in the research, commended the analysis for its outstanding quality. However, Durrer pointed out that the results still need to achieve statistical significance. Durrer stated that for Alice to be considered among the top-tier measurements of the Hubble constant, she must reach the 1% threshold, which is an immense challenge. Pisani stated that she views the work as a demonstration of a concept. With the help of upcoming missions like NASA's Nancy Grace Roman Space Telescope and Spherex Observatory, we anticipate that it will take approximately 10 more years to gather sufficient void data for comparison with the contradictory measurements of the cosmic microwave background, CMB, and Type Ia supernovae. Durrer also proposes that these arguments, which aim to resolve cosmic conflicts, may be futile, and that discrepancies in observations may signify a reality that scientists should consider. The measurements conducted by the supernova and CMB groups exhibit significant disparities, she stated. Hence, it is possible that there exists novel physics that can account for the divergence in our observations.